That's another conclusion that we know is that this for a uniform array, it has a certain main lobe amplitude, and the amplitude compared to this amplitude, the amplitude of the side lobe is for say a certain number. If you want to increase this difference, what you can do is you instead of a uniform array, you can use a triangular array, which is a convolution of a uniform over another uniform. Then you can increase the difference between the main lobe and side lobes, which makes it
That's
easier
how you
to
get to
detect.
What?
and that's how you get to the sinc squared because of the property you mentioned.
So one of the property is this is a TU rectangular convolve with a rectangular will give you a triangular. In terms, its beam pattern will be multiplied because convolution Fourier transform becomes multiplication. And that gives you the sinc square, which its main lobe has larger magnitude. The difference between the ratio between the main lobe and the side lobes become bigger, and then makes the for say sensing. You will know the main direction easier because you see a bigger difference.
Right, so, sorry, there's like two concepts that I confused for some reason. There's like resolution, which I think, is that what has to do with the side lobe height versus the main lobe height?
Resolution is
Main lobe.
resolution. You can see it as resolution is usually called angular resolution, right? So you can see it as the distance between the main lobe and the side lobe.
Okay.
Like basically,
It's also actually the side lobe width because like a very narrow side lobe means you can resolve. If you think about it, it's like what's the smallest angular. Your eyes, for instance, your eyes is all about the smallest angular resolution you can have, right?
Mm-hmm.
What's this like? Can you like resolve like 0.3 degrees or 0.1 degree as opposed to 1 degree?
Yeah, right.
That's how you get to the angular resolution because, for instance, 0.1 degrees means something at a given radius, and 1 degree means a lot more. Does that make sense? Say I have something that looks like this. So this, let's call this like H, right? And I have my array here. If my beam width is actually like very large, my E theta is actually very large, this looks like this because I don't have sufficient resolution to identify these features, right?
Is that that?
Yeah, because my side lobe is actually pretty large, so whatever I image, I'm gonna like look at all of this. If my side lobe is actually pretty narrow, I can just be sensitive to this. So, main lobe, sorry.
Okay, so when my main lobe is higher than my side
Wider.
lobe?
No, forget about side lobes for a second. Let's just focus on the main lobe. If my main lobe is like very, very fat.
So angular resolution has to do with the main lobe width.
Yes.
And I have worse angular resolution.
The fatter it is. Or wider it is.
Okay.
You can think it this way. If you're scanning,
Uh-huh.
you have the main lobe like scan
like a
things.
flashlight?
Yeah, like flashlight. If it's the flashlight is like this wide, and then I'm pointing to you, I don't know exactly where you are. I just know you are there, right? If I have a very, very narrow one, I can know, like you start to show up here, like you disappear here.
Okay.
Yeah.
So
then it's higher resolution.
think of it as like a ranging sonar. If I have a ranging sonar that has like this, I'm just identifying range, for instance. This will come up later. And I have this d theta here. So whatever range I'm going to show up, it's like the average range of everything here, right? So it's going to be very hard for me to identify something like this.
Yeah.
So it will act like a spatial low pass. As if I have something very narrow, I can just get the range of what's here.
So that's resolution, and resolution is determined by the lobe, this lobe width.
Yeah. So that's why you like your, for instance, when you have those windows, there's like very special windows. Oh, sorry. That's fine.
So then, if it's not angular resolution, what you're saying about the side lobe height versus the main lobe height?
That becomes
Crosstalk.
crosstalk.
It's not one of the things.
I thought it's like noise.
I mean
it's like signal to noise ratio.
Got it.
Main lobe is what you want. It's a signal. Side lobe is noise.
Side lobes there, it's like it means that you also get ranges from there, from other sides.
Yeah, because that's where we do the equivalent beam width or something like that.
Equivalent beam width is, how was that calculated?
Equivalent beam width, as far as I remember, is like just how much of your energy is in the main lobe, right?
Yeah, so if I have more energy in my side lobe, I feel like that's more noise.
Is that noise? Yeah.
Because what it means here is that
efficiency.
your measurement will be corrupted because you also get information from here.
So this is the one of the convolution to multiplication example, where the goal you do this is actually to increase the main lobe to side lobe ratio, similar to signal to noise ratio, so you get more energy in the main lobe than the side lobes. And another thing is, how do you calculate the area underneath this? It's actually equals to B0, because if you look at here, if you plug in U equals to 0, you're basically doing integration of the whole B over all S. You're calculating the area under the specific function of under that.
Mm-hmm.
So that becomes T0. So T0 gives you the area under the beam pattern, while B0 gives you the area after the taper function. So that's like one of the conclusions. And then this is an example of convolution. Another example of convolution is when, here we're convoluting two same things. Basically, you convolute two same things, you taking it's like second power, you square the things. Another example is if you have a uniform array, a uniform TU, and you multiply it by a phase difference, EJ 2 pi S0. What that gives you, well, I think how you draw this one is like this is like a cosine function if you draw it in real space. But if you multiply these two, that gives you the convolution in the beam pattern of the sinc function by a delta function.
Cosine is two delta functions.
Right, that's right. This one is something like that.
Okay.
So, what happens when you convolve something with a delta function is basically you're shifting the 0 to the delta position. So that's beam steering. That's the example we looked at earlier. Then another, the other way around, if we actually convolve a beam pattern, a taper function with a delta function, what does that do?
It would sample the. Oh well, you want to convolve in U space.
Yeah.
Okay, so we would multiply. Wait, the delta function is like a constant DC.
Delta function, if you convolve in any convolve is like shifting it.
Yeah.
And then, what does that do? Shifting the beam pattern, shifting the taper function in real space.
What's the question? Sorry.
So we know that a beam pattern convolved with the delta function that basically is beam steering, right? What will it be if we convolve a taper function with a delta function?
Yeah, it means that you would be moving the taper function.
Yeah, we just move the taper function, but it doesn't do anything to. Yeah, it's like moving the taper function. Does that do anything to the beam pattern?
Yeah, it shouldn't really, because it's like you're physically moving your array.
Right. Yeah.
So it shouldn't really change your beam pattern. Right?
Yeah. Oh, and then, another example is, what is the beam pattern of the delta function? If the taper function is delta function, what's the beam pattern?
Just a DC offset?
Yeah. It's like a point source, and the beam pattern of point source is uniform all directions. So these are some of the building blocks, like a taper function to sinc, delta function to DC offset, and then a bunch of things you build up with that. For say a triangular is convolution of two of these ones, two rectangular ones, those ones. We will do example afterward. But let's look at the discrete array. Discrete array, in some sense, is how you actually build a real. You can't build a real continuous array. You can only build a discrete array that's dense enough that it looks like a continuous array. So from that statement, that a discrete array, if we still look at like a line array, if it's a discrete array that there are a lot of little transducers here, if they're dense enough, its beam pattern will look like the sinc function. If they are not dense enough, it will look like something different. So what happens is, now we just have a bunch of these point sources, and then this part is what actually I never really understand, but I'm just going to first write it out.
Question.
Yes.
Did he like come up with a definition already to be what's like dense enough?
Good question. I knew that there is a minimum, which I will tell you, which is written in the end of this note. It's like anti-aliasing that we all know. If you want to sample something, you have to sample twice as fast as it is to actually figure out the exact shape, at least like some shape of it. If you're not sampling fast enough, it's not good enough. So, similarly, if you are sampling this array, you need to at least put twice dense
That's
points
what you want to resolve.
With respect to
with respect to wavelengths. So
Okay.
if you have this array, then the distance between each of the points should be at most half of a wavelength.
So it's Shannon's theorem, right? Or sorry, Nyquist.
Nyquist, yes. Nyquist, yeah. So, well, I just remember it as anti-aliasing. So, in that sense, you know how many points you need to be dense enough, and of course, the denser the better, because the denser you are, the closer you are to the real array. So, if we look at this, what it does is you're convolving the rectangular with discrete delta functions. And what that gives you is a cropped version of the delta functions. So it's basically delta function within this range now, from this to there. And what that does, and which I was not really convinced, because this is the Fourier transform of a rectangular, the sinc function, but apparently the sinc
Dirac comb.
Dirac comb, yeah, right. That thing of this delta function, a bunch of delta functions, is still delta functions.
Mm-hmm.
So what happens is you just have a bunch of sinc functions shifted in time domain, shifted and then overlapped. I have one sinc, two sinc, and something like that in the middle. And then, well, it's better I draw three, so we know one of them is like the main one. And then the distance between the main lobes, that distance, well, if it's delta u here, this is 1 over delta u,